Okay. Hi guys, this is a Productive Cloud Innovation. So we are talking today about fallacies of distributed systems. So we already discussed about the network fallacy, latency fallacy, and network as secure. I will have now my friend who's going to speak more in terms of the next fallacy. Mark, floor is yours. Mark Richards.
All right, fantastic. Thank you, Rohit. And yes, we've been talking about a lot of the fallacies of distributed computing lately. I really wanted to talk about my favorite one, specifically, Rohit, in this particular podcast, and that is fallacy number 3 of distributed computing. Again, the fallacy is something that we believe to be true, and it's not. And fallacy number 3 states, bandwidth is infinite. This happens to be my favorite one because I've actually, in my travels and gigs and clients, I've actually gotten bitten by this one. But the point is this, bandwidth is not limited. And what we tend to assume as developers, designers, and architects or analysts is that we've got plenty of bandwidth in our networks, literally gigabyte networks. And so I don't have to think about that. Turns out that especially in today's world, not in 1994 when these were coined, but especially now, this one has gotten significantly worse. And here's why. Well, we have been able to increase our bandwidth in networks. And the problem is this, we are now more and more breaking apart our applications. Let me give you a good example. If we're doing data processing within a monolith, and that's a single deployment unit, a large let's say a layered architecture. How much bandwidth are we using when we're actually internally processing the data? And of course, the answer is 0. There's none. There's no bandwidth. But now, the trend in the industry, at least now in 2020 when these are recorded, is breaking apart applications into smaller deployment units, whether it be service-based, whether we start to do more event-driven architecture, or even go as far as the fine granularity seen in microservices. And the point is this, let's break our application up into 45 pieces. Now, those 45 pieces necessarily still need to somehow communicate with one another to either pass data or to retrieve data. And so now within our processing, how much bandwidth are we using? And the answer is a lot more. Where we were actually doing 0, we're now doing gigabytes of data transfer. So let me give you an example of why this is my favorite one, Rohit. Let's say that we have a scenario which is real, where we have a wish list service. Now, this is a separately deployed service in cloud. And what it does is it manages all the wish list items on the website. It could be a movie list or wish list or whatever, but let's say it's a wish list. Okay. Now, the wish list returns all of the items and products and stuff like this in your wish list, but the contract, because of the UI, also needs the customer name associated with that wish list. You see, I have the customer ID, but I don't have the name. Now, the customer profile service has the name. So what I have to do, especially in microservices, is I now have to make a RESTful call to ask that customer profile service, by the way, can I get the name for customer 123? And it returns the name Mark. And now I've got my full contract in JSON and I send it up. Okay. Here's the problem with the fact that bandwidth is, in fact, not infinite. Let's run through this scenario, Rohit, which is real. We make, well, let me start, because there's 2 issues with fallacy number 3. The bandwidth is infinite. The first issue is associated with something called stamp coupling. Now, stamp coupling is a very old term. What it basically means is the profile service, the customer profile service, is going to give me 45 pieces of information at 500 KB, with all the customer information, including their avatar, their preferences, everything, all in that profile. All I want is just the name. 1 field out of there for 200 bytes. Okay, so think about that. If I'm making that RESTful call to say, give me the name, I'm usually going through a get on app/1.0/customer. And I'll do a get on that, and it returns me back 45 pieces of information at 500K. Whatever. It's not that much data. Do you realize we do this 2,000 times a second?
Yeah.
Wish list is accessed, which means 2,000 times a second, wish list service is making a RESTful call to profile and returning 500K of data, 500 KB of data, done 2,000 times a second. Do you realize every second that's unnecessarily transferring close to one, well, not close to, but it is 1 gigabyte
Of
of
data.
data.
Yeah, I mean, I had the
Oh,
similar problem. Like, people want to get the whole elephant, and they
yeah.
need like one partial item to solve that problem. Like,
Yep.
Google had one way of looking at, like, hey, just get one data partial item. Like, why do you need to send all the data?
Yeah.
Yeah.
And, most particularly in cloud infrastructure, this is pretty significant because we generally pay for bandwidth.
Hmm.
And so we're, if we were to solve that stamp coupling and have a separate kind of contract just to return the name that's 200 bytes long, doing that 2,000 times a second, that comes up to 400 KB. So we're talking about 1 gigabyte of network traffic and 400 KB would be all that would be needed. And this is just one out of 1,000 examples I can tell you of what I see happening when we just blindly start making all these RESTful calls in our primary API to return all this information unnecessarily. That is so much cost, and it starts to bring networks to a crawl. In a prior podcast, Rohit, we had talked about two different fallacies. As a matter of fact, we talk about fallacy one, the network is reliable, and number two, latency is zero.
Hmm.
However, the more bandwidth we use, the slower the networks go, which starts increasing latency. So now we start to see how these are really all linking together. The more we start utilizing bandwidth that was never utilized before is a shock to the network administrators. And so the point is that now they're scrambling to say, why are our networks so slow? And that's impacting latency, which in turn impacts the overall reliability because we get timeouts. So
Exactly.
yeah, this is in my humble opinion, I really do think this is perhaps one of the most significant ones. It's kind of torn between fallacy 2 and 3, but I think this is one of the more significant ones.
Great. Well, it's great talking to you, Mark, and for the fallacies of distributed
Yeah.
system, and really like the way you portrayed this, like bandwidth, and which infinite bandwidth we have. That's the way we developer try to do it. But I think the way the people have started moving is like, if I'm trying to create a data model, they look at how the customer is going to really use it. So
Yes.
based on that, they're creating the APIs.
Right.
Not
Yep.
the other way around. Oh, I have this star schema, and this star schema is going to always perform at any imaginable way you want to inner join and outer join it. That never works nowadays.
Yeah.
That's like that's another exact same thing which you are saying. Like, hey, you're trying to get it, so you have to understand how the customer is going to use the data
Yeah.
and design the APIs accordingly. Like, instead of throwing the whole basket, to solve a problem.
This is so true, Rohit. You hit a really important point on that, which is, one might be wondering, why should I really care about these fallacies?
Yeah,
Because to your point, the way we actually design our APIs is having knowledge of these kind of issues that are drawn out from these core 8 fallacies of distributed computing. Yeah. So, yeah, perfect.
great. Thanks, Mark. So I'll see you in our next fallacy.
Okay.
All right, see you. Bye.